In this example, we have a plant controlled by a proportional integral controller. We know that the proportional and integral gains are the same, which means that the controller C of S can be defined as a proportional part, K, plus a integral part, K over S. And this is equal to K times S plus 1 over S. This is the controller transfer function, again, because the proportional and the integral components have the same gain. The question in this example is, what is the value of K that will lead to a closed loop system with poles that have a damping ratio higher than 0.6? Again, we are going to use root locus to solve for this problem. Starting by finding the characteristic equation, we can get simply C times the plant transfer function plus 1 equals to 0. And that is 1 plus K times S plus 1 times S plus 3 over S, S minus 1, S plus 4, S plus 8 equals to 0. Luckily, this is the exact form we need for root locus analysis. 1 plus K times a function of S. Here we have 4 poles and 2 zeros, so n minus m equals to 2. We have an excess of 2 poles, and when you have an excess of 2 poles, we know that the asymptotes that will take those poles to infinity are plus minus 90 degrees. The centroid of those two asymptotes is the sum of all poles, that is 0 plus 1 minus 4 minus 8 minus the sum of all zeros, that's negative 1, negative 3, divided by m minus n, 2. And this is negative 3.5. Now let's look at the root locus and see if you need to determine the breakaway or breaking points. Let's start by placing poles and zeros, starting with poles. We have a pole at positive 1. We have a pole at 0, at negative 4, and negative 8. And we have zeros at negative 3 and negative 1. We also have the centroid of the asymptotes located at negative 3.5. One goes up at 90 degrees, and the other one goes down. Where is the root locus? To the left of an odd number of poles and zeros, so between these two poles, between these two zeros, and between these two poles. So clearly, these two poles will have to come together. These two zeros also come together. The poles will come together. One goes to each zero. And now these two poles, one goes to plus infinity, one goes to negative infinity. So they will also come together. They will break away. One goes up, following the asymptote. The other one goes down, following the other asymptote. The question now is, what is the value of K so that the complex poles have a damping ratio of 0.6 or higher? A damping ratio of 0.6 means that if you trace a line here, this angle, which is sine minus 1 of 0.6, which turns out to be 36.8 degrees, any points along this line have a damping ratio of 0.6. Now, how do you solve for this? We now need to locate the location of poles that have a damping ratio of 0.6. So it could be this point or that point, the intersection of the root locus and the line of constant damping ratios. This one would be very complicated to solve for because we don't know the exact shape here. But this one is easier. We have a straight line, and we know that these poles will come together and move along that straight line. Of course, that assumption is not valid around here, but it's valid as the value of K increases. Now the poles are parallel to the asymptote, and you can assume that this is the value of S on the root locus that has the desired damping ratio of 0.6. Now let's find the value of S there. to find the value of S, let's take this part of the root locus and redraw it here. So we have the constant line of damping ratios, and you have the asymptote coming down. The asymptote is located at a negative 3.5. So this size here is 3.5. This is that. This height is this height here. And of course, the dashed line here is omega n. That is the distance of the pole to the origin. This angle is 36.9.8. And this angle here is 90 degrees that we determined before. Now, looking at this angle, we can write that the tangent of 36.8 is 3.5 divided by y. And y is 4.66. The height here is 4.66. So where is the pole? Well, the pole now is here. It has always been there. What are the coordinates of that pole? That is the coordinate of the asymptote, negative 3.5, plus minus the height, 4.66 J. This is now the pole that has a damping ratio of 0.6 and belongs to the root locus. This is step one. Now that we have the pole, what is the value of K? To do that, we need to apply the same idea we did in the previous exercise. Now evaluate the characteristic equation here, add that value of S, and solve for K. So let's do that. Now, in order to find the value of K, we need to evaluate this transfer function at that specific value of S. Let's take S equals to negative 3 plus 4.66 J. We can now rewrite this expression as 1 plus K times now the magnitude of this part of the transfer function when S equals to negative 3.5 plus 4.66. Replace S in this S here. The real part now is negative 3.5 plus 1, and the imaginary part is simply 4.66. So real part is squared plus the imaginary part is squared, square root. And you now do the same for the next pole. The real part is 3 minus 3.5, and the imaginary part remains 4.66 squared. Now S is simply negative 3.5 squared plus 4.66 square root, S minus 1, and so on. And now we equate that to 0. This term here is part of the denominator. Now all these multiplications here will give a real number, and you can now solve for K, and K should be around 46.1. At this value of K, the system has a damping ratio of 0.6. You can try this on MATLAB and see if the results are comparable. They will not match exactly, and this is because of the assumption we made about a poles being lying exactly on the asymptote, but it should be pretty close. To check this on MATLAB, you can type R locus of S plus 1, S plus 3, like that, when S is, of course, the transfer function itself. And this should give the graph that you can now compare with the results you obtained here.